All right, continuing in the packet, we are on to page 14. We got some mixed practice with a focus on evaluating functions. So we've got a function f of x is 2x plus 5, and a function g of x is x squared plus x. Okay. So when we go to evaluate, we just need to plug in. So 2 times g of negative 2, so that's going to be 2. G of negative 2 is going to equal negative 2 squared plus negative 2. Negative 2 squared is 4, minus 2 is 2. So 2g of negative 2 is 4. Continuing on, 3f of 1 over g of 3. So f of 1 is going to be 3, and then 2 times 1 plus 5, all over g of 3 is 3 squared plus 3. 2 times 1 is 2, plus 5 is 7, 3 times 7 is 21, 3 squared is 9, 21 over 12, with a common factor of 3, so this is equal to 7 over 4. F of negative 2 over f of negative 2 plus 1, and then take g of that. So g of f of negative 2 plus 1. So first of all, f of negative 2, 2 times negative 2 plus 5 over, well, this one let's just do bit by bit. So that's f of negative 2. And so that's going to be equal to negative 4 plus 5 is 1. Then, so we'll have 1 over g of f of negative 2. So g, f of negative 2 we said was 1 plus 1. So we're going to take g of 2, which is going to be 2 squared plus 2, which is 4 plus 2, which is 6. So our final answer here is going to be 1 over 6. Simplify f of x plus g of x. So notice how our inputs here are just x and x. So we're just going to take our functions, f of x being 2x plus 5, g of x being x squared plus x, and we're adding them together, and then we're just simplifying. So we're going to get x squared plus 3x plus 5. So we're just sort of combining the functions. The fact that the inputs were just x means we just leave the functions as is and sort of combine them into its new function. Solve f of x equals 6. So we want to know for what value of x is our output of f of x 6. So we just say 6 equals 2x plus 5, 1 equal 2x. X is going to be 1/2. Evaluate g of f of negative 1. So that's saying put negative 1 into the f function and then evaluate g of that. So we'll do f of negative 1 is 2 times negative 1 plus 5, negative 2 plus 5. So f of negative 1 is 3, and then g of 3 is 3 squared plus 3. So g of 3 is 12. So g of f of negative 1 should give us 12. And that is all good. All right, moving on down, we have a graph of a function f of x in letters a, b, c, d, e, and h. And we're going to try to answer the following questions. So coordinates of point P and point Q. So P is going to have coordinates. If we look at P here, B is our x, A is our y. So P has coordinates B, comma A. And point Q has an x coordinate of D, a y coordinate of E. So Q, and this should say Q up here, is going to have coordinates D, comma E. So if we want to evaluate f of B, that means what's the output when the input is B? Well, when I put in B, I get out A is my y value, so f of B equals A. Solve for f of x equal E for x. So that means when my output is E, when I plug in, or when I get out E, I want to know what was my x. Well, so to get out E, I would have had to have plugged in D. So the answer is x equals D. So our next one, part D, says suppose c equals f of z and z equals f of x. Solve for x. So what we have to recognize to do this one is that c is this y coordinate here. So for some input z, we're supposed to get out c. So I have z comma c. But c is the y-intercept, so that implies here that z must equal 0. And this z equals f of x, I mean, that's a little weird. It's kind of saying, like, this is all supposed to be together. It's saying solve, it's basically trying to say solve for x when f of x equals z. I actually read this the first time thinking z was actually the function f of x itself. But I think this is what's being implied here. So it's a little tricky with the wording. But solve for x when f of x equals z. So that's saying when f of x equals z, z is 0. So it's basically saying solve for x when f of x equals 0. Well, when is f of x equals 0? That's on the x-intercept, right? That's where our y value is 0. And if we look at our graph, there it is, h comma 0. So the x value that produces 0 is h. So our answer here is x equals h. Tricky wording. Honestly, it's pretty tough to interpret, but I think that's what the problem is looking for. All right, one more piece here. So it says, suppose f of b equals negative f of d. Let's clear a little, well, d is right here. That's d. And b is here. So b and d are x values on our graph. F of b we know is a. Now, it's a little hard to see. Let's erase this stuff. Okay. F of b gives us a, right? And f of d is e. So if a equals negative e, what can we say about a and e? Well, we can say that a has the same magnitude as e. So a, the absolute value of a equals the absolute value of e. Basically, the idea being, if we were to take the negative version of e and flip it all the way back up here across the x-axis, it would correspond exactly to a. For f of b to equal negative f of d, that would have to be true. Okay, cruising along. Here we're going to evaluate composition of functions. This is a really handy tool for finding if functions are inverses. So it says find f of g of x and g of f of x. So first I will do f of g of x. So that means if I want f of g of x, that means I'm plugging in g to my f function in place of f. So it's going to be equal to, let's do a little color coding, 2x minus 3 all over 2. So notice how I've replaced that x with g of x. G of x is my input into the f function. Then I just have to simplify this down. So it would be 2x minus 6 over 2. Common factor of 2 can be canceled out, so it's equal to x minus 3. Okay, if I want to do g of f of x, let's keep this color coding a little consistent. So we'll do g of f of x. That's going to mean I'm going to put the f function into the g function in place of x. So the g function says take 2 times your input and subtract 3. My input in this case is going to be the f function, x minus 3 over 2, and then subtract 3. I could distribute and multiply and do all that, but 2 and 2 cancel when I multiply and divide, so I'm going to get x minus 3, or x minus 6. So these are not inverses of each other. They look a little similar, but they're not inverses. If they were inverses, g of f of x and f of g of x would both have to equal x. although the problem doesn't really say anything about looking for that. Okay, f of x equals negative x minus 7, g of x equals 4x. So again, we're going to find f of g of x and g of f of x. So we'll start with f of g of x. We'll do red and blue this time. Okay, so the f function says take negative your input, and our input this time is the g function. Right, that's what we're putting in here. Negative 4x minus 7. And as far as I can tell, that's all there is to do. There's really nothing else to combine or simplify. So we will say that is done. And then g of f of x, if I do g, the g function takes 4 and multiplies it by whatever the input is. This time I'm inputting f of x, so I'm doing 4 times negative x minus 7. That's my f of x that I'm inputting. It's very patriotic looking. Here I would distribute, and I would end up with negative 4x minus 28. Okay, so those would be my two results. All right, cruising along, f of x is represented by the graph below, and g of x is 2x plus 7. So f of x is on the graph, g of x is just this function, okay? So evaluate g of f of 4. So first we need to figure out what's f of 4. We need to use the graph for that. F of 4 is 6, so I'm essentially going to be doing g of 6. That means I'm doing 2 times 6 plus 7, which is going to give me 19. Okay. Next one, f of g of negative 3. So this time first I'm going to need to evaluate g of negative 3. So I'll do 2 times negative 3 plus 7, which gives me 1. And then I'm doing f of 1. So I go over to f of 1, and I see that it is 0. Okay. Solve for f of x equals 0. Well, looking at our graph, this is saying when is y, when is our output 0? And that's for these two inputs, x equal 1 or x equals 3. Okay. Evaluate f of 3 minus 2g of negative 1. Okay, so the f and g's don't really interact. We're just going to evaluate and subtract. So f of 3 from our graph is 0 minus 2. G of negative 1 is 2 times negative 1 plus 7. So that's going to be 0 minus 2 times 5. And that's just going to be negative 10. Okay. G of f of x equals 11. This one's a little trickier. So let's say that g of something equals 11, right? That's basically what we're saying. We have this g function, and we put something into it, and we get 11. So what would we need to put into g to get 11? Well, the g function takes 2 of our input x, add 7, and it produces some output. So when does that produce 11? Well, that would be when 2x is 4, x is equal to 2. So that means f of x in our case must be equal to 2. Okay, when is f of x equal to 2? That is a little tricky, because if we look at when is the output of f of x 2, we have these 2 points here. So we could kind of estimate them from our graph. We could also write the equation of our parabola. So if I start with my vertex here, I could say x minus 2 squared, because it's shifted right 2 units, minus 2, because it's shifted down 2 units, and then my a value is actually going to be 2, because I go over 1 up 2, over 2 up 1, 2, 3, 4, 5, 6, 7, 8. So that's sort of double what the x squared would be normally. Or you could plug in a point and find that. But if that's what f of x is equal to, and I want to solve for when f of x equals 2, then I can say 2 equals 2, x minus 2 squared minus 2. Add 2 to both sides, I get 4 equals 2, x minus 2 squared. 2 equals x minus 2 squared. Take the plus or minus square root of 2 to be equal to x minus 2. And x is going to be equal to, coming over here, 2 plus or minus square root 2. So this problem's pretty involved. First, we had to do g of x equals 11, figure out what input would have had to produce 11, and that has to be when the input is 2. And since our input f of x had to be 2, then we figured out, like, okay, well, what values of x make f of x 2? Had to write the equation of f of x, and then there we go. So this next one's going to be kind of similar. So it says f of g of x equals 6. So if we just replace this with x for a second, or you could use a different variable if the x is confusing. But the question is, when is our f function 6? And so we can see that's true either when x is 0, okay, or when x is 4. But the input wasn't actually x, it was g of x. So we want to know, when is g of x equal 0, or when does g of x equal 4? So we can set that up and solve. So 2x plus 7 equals 0, and x is going to be equal to negative 7/2. Or we will have 2x plus 7 equals 4, and x will equal negative 3/2 when you solve all that out. So these are two possible solutions, and you sort of have to run through that in a similar way. Sweet. Moving right along, we can go to number 5. So in number 5, we are given a function f of x by an equation. We are given a function g of x from a table, and a function h of x by this graph. So we're going to have to compare different representations. It says evaluate each of the following as possible. So our first one, f of g of 2. So g is on the table. G of 2 gives me 4. So this is f of 4. And then if I plug in 4 to my f function, I would do 4 squared minus 3 times 4 plus 1. That's going to end up being 17 minus 12 equals 5. Okay. Next one, we have g of h of 5. So this time we need to start with our inside our h function. So h of 5, if I look at h of 5, well, that gets me 0. When I input 5, I get out 0. So I need to take g of 0, and g of 0 yields 3. Okay. H of g of 4. So first I'm going to look at what g of 4 is. G of 4 yields 0. So I need to take h of 0, which is 1. G of f of 1. So this time I need to figure out what f of 1 is. F of 1 is 1 squared minus 3 times 1 plus 1, which will give me negative 1. And g of negative 1. Ooh, this one's a little bit tricky. Okay, let's write that down. G of negative 1. Now, it's tricky because our g function doesn't have a table of value for an x input of negative 1. So we wonder, like, is our domain of g of x only from 0 to 7? Perhaps. If we try to look at the g function and think of an equation, we go minus 1, plus 2, minus 3, minus 1, plus 4, plus 1, minus 3. That seems like it's all over the place. So I don't think I'm going to be able to figure out what negative 1 is. So I'm just going to say it's not in the domain, and we're going to say that is undefined for this question. Okay, g of f of 3. So let's do f of 3. That's 3 squared minus 3 times 3 plus 1. So that's just going to be 1. G of 1 is defined, and we get 2. F of h of 5. Let's have a look. So h of 5 is 0. So then we want f of 0. And f of 0 is just going to be 1. If you plug it in, you will confirm that. So that's pretty nice. Next piece says solve the following for x. So h of x equals 2. That's saying for what input of x is h of x 2? And if I look at my graph, that occurs at x equal 1 and x equal 3. Okay, those are my two options. H of g of x equals 2. So this one I need to know, like if I imagine this is h of x equals 2, I want to know for what inputs are my outputs 2. Well, we just said a second ago that that was true for h of 1 equal 2, and also h of 3 is 2 from this problem right here. However, it's not 1 and 3, it's h of g of x. So I need to say g of x equals 1 or g of x equals 3. And that's saying when is the output 3 or 1? And that's for an input of x of 0 or an input of an x of 3. So in this case, x equals 0 or x equals 3 are our possible solutions. Sometimes I like to write them just with a comma to list the solutions. Sometimes I write them separately. There's no perfect way to do it. Yeah. I mean, the other thing here, this says x is in the set of 0, 1, 2, 3, 4, 5, 6, 7. So this just means x is an element of the set 0 to 7. So it's saying that, it's basically saying that's our list of domain. This sort of means is in the set of. So x is in the set of, and we literally list our whole set, 0, 1, 2, 3, 4, 5, 6, 7. But that's our whole set of the x values. If it had only said like 0, 1, 2, then 3 would not have been an answer. Okay, h of f of x equals 2. So first of all, h of x equal 2, we already solved that. That's when h of 1 would produce 2, h of 3 also produces 2. So I want to solve for f of x equals 2. Sorry, f of x equals 1. We need f of x, the input, to be 1. Or f of x equals 3. I could go ahead and solve the quadratic. My guess, my very much hope is that it factors. So let's see, if I try to factor this, I would get x. Well, no, that doesn't look very promising. Well, let's try to solve it. So if we said x squared minus 3x plus 1 equals 1 from this one here, we would end up with x squared minus 3x equals 0. Subtract 1 from both sides. X times x minus 3 equals 0. X equals 0. X equals 3 would be solutions on that end. So that looks okay. Okay, so I'm going to write that down. X equals 0 or 3. Then I can try to solve when this is equal to 3. So I'll get x squared minus 3x. This one doesn't look so useful. We're not going to be able to factor in such a nice way. Minus 2 equals 0. Doesn't factor. You're going to be doing the quadratic formula or completing the square. I recommend quadratic formula calculator, but whatever. We'll do negative b, 3 plus or minus square root, b squared is 9, minus 4 times a times c, which is negative 8, all over 2a. So we're going to get 3 plus or minus square root of 17 all over 2. Okay. Yeah, so that's like fine, I guess. So we'll put it here. 3 plus or minus square root 17 all over 2. But you see how the quadratic formula just creeps up a lot? Like, it's good to have a method of solving that. Question J, if g of x is continuous on 0, 7, what is the minimum number of times that g of x equals 4.5? Okay, if g of x is continuous on 0, 7. Well, this is pretty interesting. So if we try to visualize this, say we have g of x. All right, here's a little graph. And say this is 7, 6, 5, and 0. Well, all our set of outputs are basically, we go 0, 3, then we go up to 1, 2, then we go to 2, 4, go back down to 3 and 1. So if we're continuous, that means we never sort of break. 4, we go to 0. Then 5, we go back up to 4. 6, we go up to 5. Right? And here's the interesting part. 7 goes to 2. So off we go. So there we go. We're on our domain. But the question is, how many times must we be equal to 4.5? And if we draw this line out, we can see we crossed it when we went from the 0.5, 4 to 6, 5. Very logical. But the sneaky thing is we also cross it when we go from 6, 5 back down to 7, 2. So there's actually 2 places that we must cross it. So it must be a minimum of 2 times. Minimum twice. Now, why did we say minimum? It's because we actually don't know what else is happening on the in-between. Like, I drew my function in this way, but there's nothing that says I couldn't have gone like 1, 2, and then way up, and then back down, and then way up and back down, and way up and back down. Like, I could have been doing anything in between as long as I hit all those points. But at minimum, like, there is no way for me to get from this point to this point without somehow at least one time crossing that line. And I can't get from this point back down here without crossing that line. So that's why we say minimum 2, but maybe it happens more. All right, a little piecewise function action. Close to done with this thing. So I have 2 linear functions. That's pretty nice. So we'll call it f of x. And we'll do our little piecewise symbol. Do my best with that. Something like this. So first of all, this function, or this slope, is up 2 over 1, 2 over 1, 2 over 1, oops. Continuing that 2 over 1, 2 over 1. So I would hit an y-intercept of 8, so I could say we equals 2x, the slope, plus 8 on the domain of -infinity all the way to -2. And it's inclusive because we have this closed dot here. Then on the domain from -2, not inclusive, off to infinity, we are going to have a slope of, let's see, down 1 over 2, down 1 over 2. So, and that is negative. So our slope is going to be -1/2 x, and our y-intercept is 6. So that kind of takes care of it. Yeah. Okay, use the function f of x below to identify the requested information. So we're going to assume this is quadratic right here. Or maybe we don't even have to. But the domain is all real numbers. It is continuous. The range, we are going up all the way to infinity, down all the way to infinity, all real numbers. We are increasing. So as we go left to right, we're increasing from here to here. Then we go down for a little bit to that vertex, and then increase to infinity. So we're increasing from -infinity all the way to -2. And then we start increasing again from 0 to infinity. Meaning we must be decreasing from -2 to 0. Our zeros, we have an x-intercept. Remember, zeros just means x-intercepts. We have -6, 0, and 0, 0. So I'll put those down. Y-intercept is at 0, 0. Extrema, we definitely have a relative min here. So we have a relative min at 0, 0. This is also a little relative max here. So we have a relative max at -2, 4. End behavior, as x is off to infinity, so is f of x. As x goes to -infinity, so does f of x. Okay, and we have opposite end behavior. And last question here, on what interval is f of x positive or greater than 0? Well, that's interesting because here it's all positive, right? And here, but we're actually not positive at this point and this point because 0 isn't positive or negative. Okay. I guess the way the question's asked also, I'm reading it as when is f of x positive, but it just says when is f of x greater than 0. But I read that as when is f of x positive. So great, so if I want to do that, I would say on the interval -6 to 0. Remember, we're describing on what x interval. By default, all these are always describing it based on the inputs. So we're positive from 0 to 6, not inclusive, or -6 to 0, sorry. And then we are positive again from 0 off to infinity, but we're not positive or not greater than 0 at that coordinate 0, 0.